Hello, my name is Kevin Garcia and I'm the computer scientist and systems engineer for this project.
My name is Isaac Pimenta and I'm a mechanical engineer on the team.
I'm Mina, optical engineer in this team.
Hello, my name is Francisco Navarro and I'm the mechanical engineer on this project.
Hi, I'm Rob Purcell and I'm an optical engineer on this project.
We're Team 24012 in charge of the autonomous mirror distortion measurement system. Caterpillar, the world's leading manufacturer in construction and mining equipment, is currently receiving many distorted mirrors from their mirror supplier. This is a big problem because these mirrors go on their vehicles and it is imperative that they meet the distortion standards in order to avoid any accidents. For that reason, Caterpillar assigned last year's senior design team to create a device that would measure the distortion of these convex mirrors and provide a pass-fail output whether it meets the distortion standards. The goal for this year's project is to automate the process of using this device while maintaining ergonomic safety of the operator and providing real-time analytics on past and current measurements.
Here is a brief explanation of the measurement concept. Since the mirror is used for heavy equipment, they are huge and convex to have a large field of view. Therefore, we couldn't use the grid patterned plate method. However, this cone is a perfect structure that can cover the mirror's field of view. The concentric rings inside of the cone will be reflected on the mirror and then detected by camera. If there is distortion on the mirror, that part won't show the concentric rings. Using this theory, the algorithm detects the radial difference between the image of the ring and the ideal contouring rings.
To successfully design our system, we set our design requirements in detail. There are 5 categories with 23 requirements as follows. First, the AMDMS shall measure the distortion of differing sizes of mirrors. Second, the AMDMS shall be able to measure the part number automatically. Third, the data from the AMDMS shall be easily extracted. Fourth, the system should be ergonomic for the operator. And lastly, the system shall be able to do this automatically.
Now here's how we developed our system from scratch. We used a system block diagram to organize our thoughts and ideas into an actual system. The way the use case works for this project is that the operator will grab a mirror and input it into our calibration cylinder and close the doors. Once they've done that, they will be pressing go on a display where it will trigger a mirror alignment mechanism that consists of 4 actuators, 4 tabs and sensors to automatically align the mirror to the optical axes. Once the alignment has finished, the camera at the top of the cone will take a picture of the mirror and send that data over to the CPU that can measure the distortion and output the result in report format.
So we have our automatic centering mechanism, and to explain how this automatic centering mechanism works, we have both a control system diagram and a wiring diagram. To give a brief overview of our control system diagram, we have our push tab sensor at the front of the actuator, and as the actuator moves, the push tab sensor makes contact with the mirror, and the sensor is then pushed on that tab, which sends a signal back to the Arduino to tell the Arduino that contact has been made with the mirror. Next, the Arduino then sends a signal to the motor controller to stop the actuators. Then once both actuators are stopped, the potentiometers on the actuators are read to determine the length of each actuator. From the lengths of the actuators, you're able to determine both the size of the mirror and the distance each actuator needs to move to center the mirror properly. The system's first minimum viable product was the accuracy of the actuators themselves. Because we want the mirror to be centered as close as possible, we need to ensure that the accuracy of the actuators is sufficient. Based on last year's testing, we had a tolerance of 1/4 inch of how close the center of the mirror can be to the center of our optical axis. And through testing, we determined that the actuators that we use are accurate to within 1/32 of an inch to the desired length. Because of that, we have determined that the actuators that are used are quite sufficient to the 1/4 inch tolerance that we need.
Our second minimum viable product was how to close the system. Unlike last year's system, we wanted to control the light coming in from the outside. However, if we used the drawer design as the previous team did, we couldn't avoid having a gap between the drawer and the cone that would allow the outside light to enter. Therefore, we had to redesign the enclosure so that it could block the light and be easy to use. The initial design was having a door that would have hinges on the outside of the door. However, the design could have a gap in the hinge parts, so we decided to use the hidden rod design.
Our calibration cylinder is so large, we had the challenge of making the rings efficiently and stacking them without misalignment. In order to make the rings efficiently, we designed the system to be cut out of a single MDF board and composed the cylinder out of multiple ring segments. In order to prevent misalignment, each ring segment had wooden dowels that would align with the adjacent layers, and we carefully glued them together.
Now, before building the whole system, there were some testing and analysis that needed to be done to design our system properly. For example, the optical system could be more improved. To reduce the system aberration, we changed the light from white LED to a single wavelength red LED light. We also calibrated the camera. By doing so, we have reduced the chromatic aberration and distortion. From a mechanical perspective, we have done finite element analysis using SOLIDWORKS. The most concerning part of our system was the base plate, since the cone, cylinder, and mirror would rest on it. Therefore, we had to verify the thickness of the base plate that would withstand the weight of the system with acceptable deflection. In doing so, we found that the base plate would need a pillar for support. After adding the pillars, we could see that the deformation of the base plate decreased.
Now, as a systems engineer, I wanted to ensure that this system was ergonomically safe for the operator. An operator-friendly system is important to consider for this because it requires repetitive actions for up to 8 hours. To ensure the ergonomic safety of the operator, we performed calculations using the NIOSH lifting equation.
Here's the SOLIDWORKS overview of the system as a whole. Externally, you can see the cone, the calibration cylinder, and the drawer box. By removing the cone and the calibration cylinder, we're able to see the two sets of actuators that will be pushing and aligning the mirror to the center position of the base plate. By removing the base plate, we could see inside the internal drawer subassembly to see exactly how the actuators are positioned and their supporting structures. Now we could look at the built version of the system. The cone sits on the calibration cylinder, which then sits on top of the drawer box. The operator would pass the mirror through the store and place it within the centering mechanism.
Once that is done, the operator can now press the Start Measurement button in the GUI to initiate the measurement. Once the mirror has been centered to the optical axis, the camera takes an image and sends the data to the CPU for analysis. At any moment, the operator can also request an analytics report from the system. By pressing the Generate Report button, the operator can have a personalized report sent to them.
Here's an overall breakdown for the total budget for the semester. Out of the $4,000 we were allotted, we will have spent about $2,200 by the time this is done. One thing I would have done differently, had I known ahead of time, is buy every item from an individual vendor in one go to save on shipping costs. We were not really close to our total budget, but I could very easily see it adding up for another team in the future.
During the course of the project, we've encountered valuable lessons that have significantly shaped our approach and understanding of successful project management. One of the key takeaways has been the vital roles played by testing, prototyping, and comprehensive documentation in steering a project towards its successful complete. These elements have proven indispensable in validating our designs, identifying potential issues early, and ensuring that all team members are aligned to our project objectives and progress.
Testing and prototyping in particular provided a tangible proof of concept and a means to determine the functionality, durability, and user interaction in a real-world context. This process was instrumental in determining and refining our system design and enhancing user experience.
Documentation is another cornerstone of our project, serving as a critical repository for knowledge, decision-making, and changes throughout the entire project lifecycle.
Furthermore, the project highlighted the criticality of our ergonomic system, just an added feature, but a fundamental requirement for developing a system that is user-friendly, accessible, and efficient.